So I will be recording this meeting if that's okay with you, Greg. So
That's fine. Yep.
yeah, we can just share to people who obviously were traveling or whatnot as well. So I guess the floor is yours, and yeah, thank you for this.
Okay, thank you, Chris. So first of all, I'm sorry for all that's happening, and I'm sorry I can't be there. I was very much looking forward to learning about gravity waves and LIGO, in part because I think there's some potential synergies with some of the things that we and other people are doing in seismology. So I'm going to talk today about work that we're doing on. It's a combination of I'll talk a little bit about data mining, but mostly about machine learning and deep learning applied to analyzing earthquake signals in order to get a better understanding of of earthquakes. And listed here is a list of the principal collaborators. These are people who are or were at Stanford, ranging from faculty to postdocs to graduate students. Okay, how do I make this go forward? Okay, so since there are some non-seismologists in the audience, at least I hope there are, I thought I'd talk very briefly about why earthquakes make an interesting target for these sort of approaches. Of course, earthquakes are important. They have societal impact. They happen deep within the earth, except for the very largest earthquakes, which rupture to the surface. And so they tell us about processes that otherwise are not directly accessible. And I think it's fair to say that they're very incompletely understood. So they remain at the frontier of science. And from the more technique-y point of view, they have interesting signals. Earthquake signals are broadband. They have certain characteristic attributes that we can exploit when we're analyzing them. And one of these properties they have is that spatially adjacent earthquakes that occur close to one another have similar signals. So we can use that and do use that in a number of ways for detecting earthquakes and analyzing earthquakes. We don't, earthquakes happen sort of on their own schedule. They happen all the time. So we have to be recording continuously, and we need high frequency information on earthquakes. So we record continuously, typically 100 sample per second, 24 hours a day, 365 days a year. The number of sensors can range from one isolated sensor to dense arrays with tens of thousands of sensors. Earthquakes in nearly all environments follow a power loss, such that as you get to smaller events, say for each magnitude unit smaller, you get 10 times more events. So there are lots of little earthquakes running around. Our field has been digital, depending on the network, since about 1990. And we weren't able to save all the data until about 2000. So it used to be we just saved the events that we knew about. We call earthquakes events, and threw the rest of the data away. We don't do that anymore. We save now all the data. We have interesting noise. In fact, most of what we record is noise. It's pervasive everywhere on Earth. There's noise. It has interesting characteristics. It's non-stationary. Much of it is comprised of seismic waves that are generated essentially stochastically. So that noise is useful, and I won't talk about how we use that noise, but I will talk about strategies for separating signal from noise. And that, I think, is where in the sort of gravity wave field, there might be some particularly obvious synergies. Okay, so I said earthquakes follow a power law. I'm going to talk about small earthquakes. We can detect the large earthquakes, that's no problem. It's the small earthquakes that we want to do a better job on. There are lots of them. So Gutenberg and Richter statistics expressed in this equation here say that for each magnitude unit lower we go, we get about 10 times more earthquakes. So if we can detect 1 to 2 orders of magnitude unit smaller earthquake, which is completely feasible with improved techniques, we can get 10 to 100 times more earthquakes. Even though these earthquakes are small, they're useful because they occur on the same faults as the large earthquake. So we can learn about the geometry of those fault systems seismologists, people like me, spend a lot of time trying to discern differences between large and small earthquakes. For the most part, we've been unsuccessful at that, which is kind of a bummer. But it means that understanding small earthquakes, the positive spin on that is understanding small earthquakes will help us understand the large ones. So all this is, these are reasons why we study small earthquakes. There are different ways to get better recordings of small earthquakes. One is illustrated with this figure. This is Japan. So can you see my cursor where I'm pointing?
Yep.
Yeah, okay. So this is the main island of Honshu, Shikoku, and Kyushu there. This is 3 years of seismicity from 1992 to 1994. And this is taken a decade later. You can see there are lots more earthquakes, including red, or the red symbols, which are a different kind of earthquake. The difference here is not that suddenly earthquake activity got much more active. It's that the Japanese improved their recording network. So they went to a high sensitivity seismic network and discovered new kinds of earthquakes, many more earthquakes, and just got a much deeper look, more detailed look at what's really going on at depth under the Japanese archipelago. So that's a hardware solution to getting a better catalog. From here on out, I'm gonna talk about software solutions to getting a better catalog. So earthquake monitoring is something that's done around the world. It's done at the global scale, it's done at the regional or local scale, it's done in mines, and it's even done in the laboratory. And wherever it's done, basically the processing is similar. We want to detect, locate, and characterize those earthquakes that occur as completely as we can, and locate and characterize them as accurately as we can. So if we solve it at one scale, we can easily transport that technology to other scales. Our data, as I mentioned before, are seismograms. Typically, we record the velocity of ground motion versus time. Our sensors, typically, we like to have 3 components, so vertical, north, and east, for example, to get the full vector motion with time, and these other things I mentioned before. So we have a lot of data, and it's coming in continuously. So our workflow for developing earthquake catalogs looks something like this. We have a bunch of seismograms, so this time increases from left to right, and these are organized by distance from where this earthquake occurred, which would be at 0. And you can see the fast arriving P wave, a slower arriving S wave. We'll get back to that in a little bit. But with data like this, these data are telemetered to a central computing facility. Some sort of pre-processing is done, perhaps filtering to reduce noise. We detect events. We pick the arrival times, like the P and S waves. We time them very carefully. We associate them between different stations within the network to figure out whether or not they represent an earthquake or whether it's some local noise source. Assuming they do, we locate those earthquakes and we calculate their magnitude and so on and so forth. So the output, just shown in map form, would be an earthquake catalog, such as shown here for a month of earthquake activity in California. So that's what we want to do, and we're going to use techniques of data science to improve this. So the baseline is sort of the standard approach. So the detection, we usually, it's illustrated here, what is typically done. So again, time increases from left to right. This is ground velocity with time, and you can see it starts at 1040, some arbitrary time, since the earthquakes are happening on their own schedule. What we do with this time series is we rectify it, we square it, and we take a running short-term average divided by a long-term average, and that statistic is what's shown at the bottom. And when that number gets above an empirical threshold, our algorithms say, hey, there might be a seismic phase here, and we do that over all the stations. And then if those phases are consistent with the propagation velocity of waves within the Earth, we associate them with a single event, and then we process that event. So this technique works pretty well. It's tried and true. It's been used for many decades, and earthquake catalogs are built upon this sort of straightforward process. And it works well. So provided events are recorded at 3 or more stations, such as that we can associate phases, then they'll make the catalog. The events have to be impulsive. This statistic is, as you can imagine, is just looking for an impulsive arrival. And it works well provided the events don't overlap in time. If they're closely spaced in time, that causes problems. So it works less well, the standard approach, when the events are emergent. So what's shown here are P and S waves from 3 different low frequency earthquakes. These are small, weak events that were discovered in Japan less than 20 years ago. There are now millions of these things recognized around the world, but prior to this discovery paper, they weren't in earthquake catalogs at all. And the reason they weren't is because the standard approach doesn't capture them. This is that same seismogram I showed you previously with the nice clean looking earthquakes in them, but there are a number of smaller earthquakes that are much harder to see. I put these red ovals around them. These are small earthquakes that are nevertheless interesting and important. But because they're small and because their arrivals are weak, they may not rise above the threshold for the phase detection, and they may not make the catalog. And here's an example of an earthquake swarm in New Zealand. So time increases from left to right as before, but here there are many, each one of those lines represents a half hour. So this is like a day's worth of record. And what you can see is that there are lots and lots of earthquakes and that their waveforms are strongly overlapping. So just at the time when lots of things are happening and information is pouring out of the earth, our current algorithms have trouble keeping up. So that's not a good situation. We'd like to improve that. So there are different approaches for earthquake monitoring. I'm going to talk about most of these, not quite all of these, but one approach is to use techniques of data mining that exploit the fact that nearby earthquakes have similar waveforms. So I'll talk about template matching, briefly about page rank, that is clustering, and then a little bit more detail about our algorithm FAST. And then we'll turn to supervised machine learning for earthquake detection, for denoising, and for picking phases. I'm not going to talk about self-supervised learning, but our group and other groups are exploring these sort of methods for things like discrimination as well. Okay, so this is data. So again, a seismogram going from left to right. This is 5 seconds of record, so 100 samples per second sampling. These are, I think, 38 different earthquakes. So these occur at different times over a period of several decades. They're small events. This is less than magnitude 2. And what you can see is that for those 5 seconds of record, the wiggles, the earthquakes waveforms match wiggle for wiggle. And that's emphasized in this bottom trace where I've actually lined them all up and superposed them. And you can see the line only gets slightly wider. These are almost exact repeats. So if we're looking for a repeat of this earthquake, we could do much better using this as a match filter, or what we call a template in seismology. Using it as a template and scanning through continuous data to find a repeat of that signal. That's much more sensitive than using something like the STA LTA that I talked about earlier. Okay, so repeating earthquakes don't occur everywhere. They're interesting for a variety of reasons. But what's shown here, this is on the same fault, the Calaveras fault that's near San Jose, California. And these are now thousands of earthquakes. So rather than show the time series with the wiggly lines. I'm showing them in color. So shown here are 3,500 seismograms ordered by distance along the fault and color coded in blue or red, depending on whether the ground motion is positive or negative. And what jumps out at you from this figure are all these stripes. So the stripes that go through the waveforms have different slopes depending on where you are. Those stripes are there because adjacent earthquakes aren't identical, but they're pretty similar, wiggle for wiggle. So again, even though they're not exact repeats, we can use that similarity to develop a powerful earthquake detector. And that's what template matching does. So this is possible because the Earth structure changes essentially not at all. These adjacent earthquakes have similar waveforms, so we can exploit that to find more earthquakes. And so this was published in 2006, not really that long ago, by Gibbons and Ringdahl, in a very nice paper showing how powerful this sort of technique can be for finding small earthquakes in noisy data. So we applied this to low frequency earthquakes in Japan, and we're able to show that a phenomenon of a weak shaking called tectonic tremor is actually a swarm of tens of thousands of small low frequency earthquakes. And the way we did it is we took this low frequency earthquake signature shown in red. Each one of these three sets of seismograms is recorded at a different seismic station, shown here with triangles. And this is the north, east, and up, down components of motion. It's the signature of that a low frequency earthquake in that location. So we develop a detection statistic, which is basically the running dot product of that through the continuous seismic data. That's shown here. It's the detection statistic is the sum of that quantity. I don't know if you can read it, but each of these numbers is small. It's sort of a weak correlation, numbers like 0.43, 0.06, 0.48, but every single number is positive. And so you can calculate the probability that that's due to chance. It's like 1 in a billion or something like that. And so based on that, we develop a detection threshold, and this represents a positive detection of a low frequency earthquake in that approximate location. So a nice property of this, so it has a low type 1 error rate, that is a low false detection rate. It also is very sensitive. So even if we take a known low frequency earthquake shown in red with its amplitude divided by 10, so a signal noise ratio of approximately 1/10, embed it within our original waveform, and then try to detect it, we detect it over 90% of the time. So I think 33 out of 36 or something like that. Anyway, it's even for weak signals, if we have just a nominal network of 8 or 10 stations, we can detect reliably at a signal noise ratio of 1/10. And that's because we know wiggle for wiggle the signal that we're looking for. Okay, and so we were able to use this to, we and subsequently others were able to use this to sort of decompose this otherwise sort of diffuse looking signal and figure out the behavior of this tremor. So the tremor is comprised of low frequency earthquakes. These are earthquakes that are slow relative to ordinary earthquakes. That's why their signature is weak. The inertial term is a little less dominant in the wave equation than for regular earthquakes. And so we developed a scaling diagram showing the log of the characteristic duration of an event on this axis and the log of the seismic moment. So that's a physical measure of earthquake size that seismologists like to use. For ordinary earthquakes, the slope on this line is 1/3. That is, they grow as the cube of their duration. Slow earthquakes, the low frequency earthquakes, as well as other types of slow earthquakes that have been discovered by others, grow linearly with their duration. So this was presented in 2007. It's empirical, right? It's not based on an understanding of the physics that underlies this scaling. So we're still working on that. And I thought for this crowd, it would be interesting to compare it to the Hertzsprung-Russell diagram that was presented in 1912. It too was empirical. There was not yet a physical understanding, but it was understood 25 years or so later to be to result from stellar evolution under fusion. So we're sort of in between 1912 and the 1930s in developing that understanding for our scaling diagram. Okay, so template matching is extremely effective. It can be scaled up to the largest available scale. So this was done by Ross and others for the Southern California region. So Southern California is one of the world's best studied earthquake zones. It has a lot of earthquakes. It also has a lot of seismologists that are paying close attention. What Ross et al. Did was to take all the digital waveforms they had of known earthquakes and scan all of them against all the available continuous seismic data. And it's shown in various ways, but basically they find 10 times as many earthquakes as are in the catalog. So an order of magnitude more earthquakes. And these next two figures show the difference that makes. So this is zooming in on the San Jacinto fault, which has 3 branches here near Anza. So its location is shown here. This to its east is the San Andreas fault. But the San Jacinto fault is moving just about as fast as the San Andreas at this latitude. So it's a very active fault. This is the standard catalog, and the template matching catalog just has much, much more information. Actually, in this area, more than 10 times as many earthquakes. And if you flip back and forth, you can see how previously dispersed earthquake locations, once you sort of fill it in with more earthquakes, you find many, many more planar linear structures that are the faults that we think these earthquakes are occurring on. So this isn't using any extra data, it's just using a better approach to analyzing data that we already have. And so we can reap great benefits by doing this. Now, there's a question that may have occurred to you. What if we don't have templates? So templates are going to are known earthquake waveforms that we want to find things that are similar to them, and we're talking about a pretty strict wiggle for wiggle similarity. If we don't have the template, we won't find the match to the template. So we can do this naively, do an uninformed search for similar signals by basically comparing all times with all other times, just shown schematically here. That works. It's computationally intensive, but it works. And the fact that signals repeat not just once but many times, particularly in tremor, allows us to find more reliably templates from without sort of prior information. So we used PageRank. This is one of Google's early ranking methods to find hierarchical relationships within waveform similarity measures, and it works well. The problem is that these naive all against all methods don't scale. So we can't apply them to very large data sets, that is years or decades, because the computational effort scales with the square of the time considered. So very quickly, it becomes infeasible to apply these methods. And here's where we start getting into real big data technologies. So there are technologies that do similarity search, not exactly, but approximately, and they are designed to be computationally tractable. So the one that inspired us to do this was the Shazam algorithm. That's one to identify songs from a short sample of a recording. I was in a store and I heard a song I was interested in. I turned on Shazam. It listened for 10 seconds, made the match somewhere out on the cloud and tried to sell me the song in 15 seconds or something. It's amazing. And that's sort of what we want to do with earthquake waveforms. There are other algorithms for doing this, where they're in businesses where there's real money, like copyright infringement. So we're basically piggybacking on those big data technologies to study earthquakes better. So this is Clara Yoon. This our method is, we call it FAST, for fingerprinting and similarity thresholding. The idea is, just like a fingerprint is a compact representation of a person like Clara, so too we can develop a binary fingerprint of a complex set of wiggles like an earthquake waveform. So that's data compression, which we do, but we have to be careful to not just make it sparse and compact, but also that it be diagnostic. That is, similar signals have to look similar in their fingerprints, and they have to look different than noise. So once we get that fingerprinting done, we store them in a database and search that database efficiently. So here's our processing pipeline. It's only a part of the whole earthquake catalog pipeline. But the idea is that we window the data, we take the Fourier transform of the waveform, it gets its spectral amplitude, we take a wavelet transform of that Fourier transform, so a transform of a transform, and then we carefully select those coefficients that are most different from their average. That's sort of the key step in making it diagnostic, and we make a binary fingerprint out of that with using just the sign of a small subset of the total coefficients. So we then use a technology called locality sensitive hashing to store these in a database. That is all the waveforms from some time period of interest. So the longest duration time period we've used is 11 years. We then query that, we then go through the waveforms again and we query them, and we find, the analogy I like to use is it's like we're putting, the database is like a filing cabinet, and we're looking for folders that have similar events within it as determined by their min-hash signature. So we make the match and we find the similar waveform, and our search is done. And then we go through our post-processing. So let me illustrate the advantage of this sort of approach with an application, and that is a so-called induced seismicity or human-induced earthquakes. There are a lot of different ways in which people cause earthquakes to happen. The most prominent of these is through injecting fluids in the subsurface. Recent earthquakes in Korea and China that are known to be induced have been big enough to cause damage and to kill people. So this is a real problem for people, obviously, and for the industries that are developing, are trying to develop unconventional hydrocarbons. So you may have heard of fracking or hydraulic stimulation. That's a way in which a well is drilled first vertically and then horizontally into a zone, a geologic formation that has hydrocarbons in it, either gas or oil. And then from one end of that, what's called a lateral, the toe, back towards the heel, they sequentially do hydraulic stimulation to create permeability such that the previously what's called a tight formation now has permeability, and the hydrocarbons can be extracted. That can trigger earthquakes. Another way that earthquakes can be triggered is that in dewatering operations or flow back water from this process, some of the water comes back out. They then inject that water deeper because it's full of salts and other nasty things to dispose of it, and that too can trigger earthquakes. So we'd like to, these earthquakes are potentially dangerous. We would like to understand them. They're sort of an experiment for us, and the industry is interested in managing the hazard and the risk that they pose to their operations and things around. So we're going to take a look at Guy Greenbrier, Arkansas. I should have made a better map. Arkansas is sort of in the middle of the US. So this is the state of Arkansas, and we're going to zoom in. This here is a zoom in that red square. So in 2010, 2011, this area had a sequence of induced earthquakes culminating with the largest one, a magnitude 4.7, that caused some of these wells to be shut down. So there are two kinds of wells in these regions. The downward pointing ones, these are the wastewater injection wells. Those are the deep ones that are disposing of fluid, not the hydraulic stimulation wells. Shown in gray are where the earthquakes will eventually occur. Shown in color are where earthquakes occurred in the summer of 2010 when the sequence was just getting started. So what we wanted to do was to figure out how this sequence got started, and could we have recognized that a larger sequence was going to follow. And so we applied this FAST method. Here's our catalog, 75 earthquakes. You can see the magnitudes are small. In the summer of 2010, we ran FAST on the catalog, did template matching in addition on some of the templates that we identified with FAST, and we increased the number of earthquakes in the catalog by a factor of 200. So from 75 to over 14,000. And suddenly we're seeing earthquakes not just here where the gray things are, but dense clusters of earthquakes in other locations. If we zoom in on this one here, this again is one of those color plots showing over 3,000 earthquakes in that one little cluster. Here's an example of the east-west time series. Time goes from 0 to 8 seconds. And most of these earthquakes are too small to locate because they're only recorded on one station, but a subset of them are recorded on enough stations to locate 667. And when we locate those, we see that they trace out and they trace out in space and in time hydraulic stimulation within these wells. So this very clearly, unambiguously ties these earthquakes to hydraulic stimulation. So by applying FAST, by detecting more smaller earthquakes, we're able to suddenly gain an understanding of earthquakes that were otherwise very sparse and obscure. So I've talked about template matching. That's a form of informed search. I've talked about FAST. That's this LS. That's locality sensitive hashing. That's an example of uninformed search. What we'd like to do is to get away from this strict similarity search to more permissive search in terms of the characteristics, and we use machine learning for that process. So I'll skip over these. I mean, I've talked about the size of seismic data sets. That provides new opportunities, actually a need for new methods. There are lots of progress on machine learning algorithms and models. Seismology is benefiting from that by keeping up or trying to keep up with those developments. And the bar to doing this sort of thing is lower than ever. So GPU computing is really useful particularly for training these networks and for using them. And packages like TensorFlow and PyTorch are allowing us to focus on the data, the sort of data wrangling aspects of things rather than coding the neural networks from first principles. This is from a review paper we published. The notion here is just that machine learning in general allows us to explore hypotheses or learn relationships in a way different perhaps than how we've been trained to do that through our standard education. Skip that one too. Okay, so an advantage in seismology over some fields at least is that we have very large labeled data sets. So here's an example of a seismogram. We have P waves, S waves, and a dispersed surface wave train. We have lots of labels. We have tens of millions of labeled waveforms like this, but those labels are far from perfect. And so we have to do some quality control on them and add labels as well. So here's a data set that we put together, published late last year in an IEEE journal, where we take only 1.2 million seismograms of local earthquakes and noise recorded around the world. Excuse me. We spent a year doing quality control on this data set. We added lots of labels. We put it in a data science friendly format so that non-seismologists could, just sort of load it and start playing around with it. The idea is we want to get data scientists, non-seismologists, interested in the kind of problems that we're working on. So some of the data issues we had to work with is there are times when there's supposed to be an earthquake in the data, and yet there isn't one. So this would be an example of a bad label, and we wouldn't, if we trained a network with these kind of data, it wouldn't work as well as it should. Sometimes there are extra earthquakes. So here's an earthquake that's labeled. Here's a smaller earthquake that's unlabeled. And so if we have small unlabeled earthquakes in the data, and we call those noise, that's a problem, because the algorithm would learn to ignore those small earthquakes when in fact that's probably what we're looking for. And there are examples of blunders in the catalog. So here's a pic of a P wave in blue. It should be right here. It's the first arriving wave, and yet there's an error in the catalog. That too will undermine deep learning algorithms because it's a bad data. Anyway, this was published in IEEE Access. It has some intro seismology material in it. And again, the idea is to get data scientists interested in earthquake research. It has only local earthquakes. So there's much more work to be done with larger earthquakes, more distant earthquakes, quarry blasts, other kinds of seismic events, but got to start somewhere. Okay, so back to our earthquake monitoring workflow. I'm going to show 3 examples of how we can use machine learning to improve things. And I'll start with event detection, which we've talked about already. So CRED stands for Convolutional Recurrent Earthquake Detector. And the idea behind CRED is that we use convolutional layers to capture features, the sorts of wiggles we have that characterize seismic waves on the seismogram. And we use recurrent layers to efficiently capture the sequencing of those phases. So we know from elastodynamics that the P wave comes first, then the S wave, then the Rayleigh wave. And the idea behind the recurrent layers is to capture that, that sequencing. There are other ways of doing that. We're experimenting now with dilated networks, so-called TCNs, but this is what we use in this application. And so it's not a terrifically deep network, 12 layers, 250,000 trainable parameters. We use about 500,000 3-component NCSN stands for Northern California Seismic Network seismogram, so that we did not use, this is published before the other paper, we didn't use the global data set. So all these data are from Northern California. And what we're trying to predict, the output of this, the network illustrated on the left, is a 0 if it's not an earthquake, and it's a 1 if it's an earthquake, from the earthquake first arrival, shown here, to the the scattered waves of the earthquake coda. So 3 times the S minus P time, which is the difference between the blue and the red. So that's the output of our detector. And so this is, with these 500,000 examples, it's learning not the wiggle for wiggle match, hopefully, but the characteristics of the earthquake waveforms that can be used to generalize to find other earthquakes. So it works. Here's an example of applying it to local earthquakes. Ground truth is shown in blue, and the prediction is shown in purple. It works well, as it should, for this nice clean local earthquake. It works for regional earthquakes where the signals are a little more spread out because the waves travel at different wave speeds. It works for what we call teleseisms. These are distant earthquakes where the waves are diving through the Earth's mantle. It's able to find those as well. Importantly, it works acceptably well, not perfectly, but acceptably well at low signal to noise ratios. This is important because these are the earthquakes that we need to detect, that escape detection, sort of standard approaches. And I don't know about LIGO data, but seismic data, there's frequently bad channels or dropouts of channels. So we train it in such a way that it will be robust with respect to them. So this middle channel, the north-south channel, this is not operating properly. There's, I don't know, water in the line or some problem with telemetry. And so it's full of spiky signals that an STA-LTA algorithm would identify as an arrival. And the neural network is smart enough, like a seismologist, smart enough to ignore that bad data. Other kinds of more pernicious bad data, it's also able to ignore because it's been trained in to recognize true earthquake signals. And it actually improves on ground truth. So it finds multiple events when they occur because of the way we trained it. And it improves on the duration over what's in the earthquake catalog where errors can creep in. Okay, so machine learning works quite well for event detection. Phase picking is another important activity that seismologists engage in. So we developed a neural network for picking those phases. So this again is a seismogram. This is the east-west, north-south, and vertical components of motion. So our output from this neural network is put into 3 categories. It's either a P wave, the first arriving wave, so that the pick from the catalog is shown in blue. That's what we take as ground truth. It's an S wave, the arrival there is shown in red, or the complement is that it's noise. And so we train this, we engineer it so that it peaks the probability of the output at the measured arrival time, measured by network analysts, of each of these seismic phases, and then we have a truncated Gaussian of 0.2 of a second duration on either side. If we were to do this more rigorously, we might change that probability based on the quality pick uncertainty, but we just did the simple thing and use basically a constant measurement error assumption. Okay, and again, we trained it on a large label data set, again, initially from Northern California, though we've since retrained it. So we have 750,000 PNS picks to work with and their corresponding waveforms. And the idea is we're classifying those waveforms as either P waves, S waves, or noise. And as I said earlier, we design the probability so it peaks at the earthquake arrival time. So an advantage over conventional approaches is that this, unlike STA-LTA, it separately classifies P and S waves. That's a big advantage because for a real earthquake, the P wave will come first, the S wave will come second. So that helps us with association. Lots of our data is clipped, such as this example, due to either sensor limitations or limitations in the telemetry, which is the case in this instance. It works well on clipped data because we train it on clipped data. So just like a seismologist, it recognizes change in frequency content here in this clipped time series as being diagnostic of the S wave arrival. And we train it on noisy data too, so it can see through the noise and make the picks. We don't try to remove the noise ahead of time. And we can test that using sort of standard measures so this is PhaseNet, that's our neural network. For the P wave pick, this is the residual, nicely centered on 0. It's got a symmetric distribution. The standard approach has a little bit more dispersion and it's skewed towards late arrival times. So that will lead to biases in location. Not too bad for this case. It's a pretty narrow distribution. Where the network really shines is in picking S waves, which is much harder to do. So the S waves are not the first arrival. And you can maybe see the axis here, it's 14,000 versus 1,600. So a much higher peak, many more S waves, pretty symmetric distribution, maybe a little bit of late skew, but nothing like the standard approach, which really has trouble with S waves. Some of that dispersion comes from, comes from bad picks in our so-called ground truth. Our ground truth is not absolute. The analyst reviewed picks have errors in them, such as this bad P pick. You can see that PhaseNet does a better job. of picking that arrival time. And here's a truly terrible S-pick. I don't know what's going on. It should be here, but it's looks like maybe a 1 second error in that S-pick. So we have a little bit of an issue here in that our ground truth is somewhat squishy. We don't have absolute ground truth. We need to resort to other methods. So here's an example. These are small earthquakes in the Apennines of Italy. Locating using hypo-DD, that's sort of similar to what in astronomy is adaptive optics, so locating earthquakes using differential times. If we picked by our standard method, is shown at the left, and this is in 3D, depth is in the vertical direction. This is using our machine learning based picking. Our prejudice is that earthquakes occur on planar faults, and so the PhaseNet results better meet that prejudice. It's not absolute ground truth, but it's reassuring that we're getting better picks out of the machine learning based method than standard methods. There are other ways we can use a cross correlation of similar waveforms, which is the gold standard for getting accurate picks, and look at those differential times and compare them with these. And when we do, we see that PhaseNet, this is for P waves and for S waves, gets the dispersion is just a few samples about the mean, and the mean is nicely centered on 0. So it does a very nice job of, as far as we can tell, of getting an accurate arrival time. Okay, so that's PhaseNet. The last thing I'm going to talk about, I'm going to go backwards. I'm going to talk about pre-processing, or what we call denoising. Now, this is where I think the synergy with gravity wave detection might be the strongest. So if you haven't been paying attention now, and you're interested in that kind of thing, now's a good time to tune in. So here we're training a deep neural network that we call deep denoiser. So this really is a deep network with many, many layers. It's got the usual skip connections and whatnot. Our data are a small, modest number, 56,000 high signal noise earthquake waveforms and 180,000 noise waveforms. Now that's not really as much as you'd like to train a very deep network like this. So what we do is we augment the data set by expanding it to nearly 1 billion examples. And the way we do this is that we recombine the signals and the noise, and we vary the signal strength to teach it to find weak signals and noisy data. So we sort of artificially, semi-synthetically create many realizations of weak signals in real noise in order, where we know the labels, because they're based on the high SNR earthquakes, to expand the training data set by many orders of magnitude. And what we're solving for is this. So this is our time domain signal on the left. It's a combination of signal and noise. We want to divide it into signal and noise. And so the way we do that is we take the Fourier transform. So we take the complex spectrum, and we develop a mask, which is in this time frequency space. It's just a bunch of real numbers or weights that pass through or don't pass through these complex numbers. So we don't mess with the phase. We just create a filter, if you like, in time frequency space that this one sends through the signal, this one sends through the noise, and we train it with nearly 1 billion examples. And so here's our mask results. And this is the inverse transform, where we hopefully, to the extent possible, recover time, recover signal on the top and noise on the bottom. Okay, so I'm going to show pretty quickly a number of these examples. Here's our clean signal, and here's a zoom in on the initial part of it. The second panel is noise, and this is the sum of the two. So we've just added them, superposed them. And this is independent data that was not used in the training, but that we use to test, validate the method. Here's our recovered signal. It matches the original signal quite well. If we zoom in here, you look at the first arrival, you can see there are differences. It's not identical, but it does much better than just say straight filtering would do. Here's our recovered noise. If you look closely at the noise, you'll see that the noise amplitude from when the signal is high, it's a little bit weaker than the noise amplitude in the original data. So there's some crosstalk. But again, by doing this in the time frequency space, we do much better at separating signal and noise than other methods. This shows the same thing in terms of spectral amplitude. Again, the recovered noise, you can see there's weakness relative to the original noise when the signal's coming in. That's another measure of that crosstalk. But this method works really well on earthquake signal. So here's another example, clean signal added to noise. Here's the recovered signal. It matches the original signal pretty well. Another example where it works pretty well. We try to trick it by just sending it a bunch of noise that's kind of spiky. It's smart enough to recognize that that doesn't have the time frequency characteristics of an earthquake, and so it must be noise. So we can measure various ways in which this increases performance. So one is using the old STA, should be STA, not STLA, STA, LTA detection statistic. The noisy data, it does poorly. The denoise data, it does exceptionally well. So we could, if we wanted, use this for routine processing. It helps avoid false detections, such as these spikes in the time series that have the wrong characteristics. I'll show a series of these. In terms of the signal to noise ratio and its recovery, this is shown in decibels. Larger is better. Deep denoiser is the red crosses, and you can see it outperforms other methods like generalized cross-validation and regular filtering at all levels of signal to noise. So we're looking at decreasing signal noise going from left to right. Eventually, the noise wins, but it does, deep denoiser does a much better job of recovering the signal up until that point. Arrival times are critical to seismology, earthquake location, so smaller is better. And so you can see here, we stay closer to 0, again, until we get to very low signal to noise ratio, and then deep denoiser 2 fails. But there's a lot of data in this signal to noise band because there are a lot of small earthquakes. So this is going to help a lot. And it recovers amplitudes better. That's important for magnitudes. So there are many potential applications of this. Any earthquake monitoring would benefit from this sort of thing, particularly in urban locations, noisy locations like cities, like the ocean floor, like volcanoes, and who knows, perhaps there's an application to be had here in LIGO where you can detect weaker signals within noisy data. So I'd argue that we're on the threshold of being able to do comprehensive earthquake monitoring using machine learning. I'd like to show a few examples of that. So this is Fairview, Oklahoma. This is an induced earthquake sequence. These are earthquakes that happened in 2016. If we use sort of state-of-the-art template matching data mining technique, we recover 4,800 earthquakes. That's a lot, and that led to that's a great improvement over the original catalog. Deep learning increases that by a factor of, what, 5 or 6. And importantly, it fills in the gaps in places where we don't have templates in a way that template matching just can't. So we discover many more earthquakes and a more complete view of where earthquakes are and are not occurring in this induced earthquake sequence. Here's another example from another obscure place in Oklahoma, Cushing. This too had an induced earthquake, a magnitude 5 induced earthquake, and we can see lots more structures active, factor of 5 or so more earthquakes in the deep learning catalog than in the already quite good template matching catalog. Pawnee, Oklahoma, here it's nearly an order of magnitude more earthquakes that we get, and that's largely because the network is less good here, and so improved approaches have more of an impact. So these machine learning methods, it takes a lot to train them, but once they're trained, they're faster, they're easier, and probably most importantly, they're more general than data mining methods, and they result in a more complete picture. This is work in progress. It's joint with INGV, British Geological Survey, and Lalonde and Stanford, where I am. This is a decade-long sequence of earthquakes in the Apennines. Our deep learning-based earthquake monitoring applied to these data has found over 500 million well-located earthquakes so far. We think that number is going to go up. And there's just unimaginably rich structure and information on earthquake processes that the challenge now is to extract that from this very large derived data set. So for seismology, I'd say that the standard practice that we're using around the world now is less than optimal. I think we're poised, ready to go with AI-based methods, certainly for detection and arrival time picking, and eventually to extract AI meaning from the results using unsupervised learning. Right now, I think what the first steps will be to sort of do sort of plug in for detection and association and so forth, just one at a time. But eventually, we'll be using the network itself as the sensor and merge these different processing steps in the workflow, and that's really going to revolutionize seismology and our ability to find small earthquakes and extract meaning from earthquake catalogs. So with that, I'll stop. I hope you find this useful. I'd like to thank you again for this opportunity and mention that the published algorithms I've talked about are available at the following locations on GitHub. Thanks very much.
Thank you so much, Greg. It was very insightful. I see there's some questions in the chat.
Yeah, so that's this orange thing, chat. Okay, great.
So basically one of them is there's 3 questions from Alberto. So
yeah, okay.
Do you want to have
first question is,
yeah.
So first question is, this is from Alberto, how do results in convolutional neural networks for event detection with spectrograms in CNN compare to those with time series? Well, I don't have a direct comparison for you. We're using, we just yesterday submitted another paper that's sort of an update to CRED, so the convolutional recurrent earthquake detector that we published last year. And this new method actually, it's a neural network with multiple outputs that allows, that both picks the earthquake waveform and the arrival times. And so by doing it, and does it in the time domain, and by doing it that way, you can use the context of the earthquake waveform and the individual phases and their sequencing together to get a better answer, and it outperforms all these other methods. So I can't answer your question directly, but I just would say that it's sort of a moving target. For earthquake detection, I don't think there's a great advantage to working in the frequency domain. For denoising, I think there is, because the noise and the earthquake signal have very different, for the most part, have very different characteristics. So for separating those two, I think that's really helpful. Okay, so next question, also from Alberto. What factors may determine the time from the arrival of the P wave and that of the S wave? So what determines that is the distance from the earthquake and the particular geology of the part of the Earth's crust that's involved. So the farther you get from the earthquake, because P waves travel faster than S waves, the more space and time between the two. And we, presumably these neural networks are sort of encoding that in their recognition of seismic phases. So I'm not sure that answers your question, but
Thank you.
Pardon me?
Yes, make the information show. How do you use template for the
There's something, I'm having a problem with your audio. So maybe you could, I'll just keep going down the, because
Okay.
I couldn't hear what you said. I heard that.
Wait.
Okay, now it's good.
Yeah, it's perfect now. Yes. No, it's bad again.
Wait. Now it should work.
Now it's fine.
So the third question, to make it shorter, how do you build this template bank for the matched filter? Because I was quite impressed by the fact you showed similar waveforms at the same station, I guess. Is that only because the earthquake is at the same location also, or why does this happen?
Yeah, that's exactly right. So the point of showing that was actually a repeating earthquake. So the same little piece of fault rupturing repeatedly. And the reason I showed that was to establish the fact that even over decades, the Earth's structure doesn't change. So we can use, you can use a bank of templates to find earthquakes throughout all the data that we have.
Right. Thank you.
Of course. Okay, so there's a question about whether we've been using transfer learning. The answer is not yet. So we have tried applying, the different algorithms, PhaseNet in particular, in diverse environments. So we've tried it in Italy. We tried it in Arkansas. We tried it on OBS data from Mayotte and from off the coast of Oregon from axial seamount. In all those cases, we didn't have to do any transfer learning. It already worked well enough. So we were sort of prepared to do that transfer learning, but we didn't have to. With the denoising, if you were to apply that in a city, I think you probably, where the noise characteristics are very different, I think you'd probably have to do transfer learning. But the answer is we haven't done that yet. Okay. So
Thank you.
Of course, yeah.
Okay, I guess. So I guess that's it. I guess from the feedback, people are excited here. I mean, you've managed to get basically some thoughts going, and hopefully people, I think, yeah. So hopefully they can potentially transfer some of these ideas back into the hackathon that we have. So
yeah, I would really love to be there to help, inform that. Failing that, if anybody has questions about these algorithms and how to adapt them to LIGO data or whatever, I'd be happy to try to answer them.
Yeah, so what we're doing for the hackathon here is we actually give them some earthquake data, and they're trying to classify what type of earthquake they have.
Oh, cool.
I can share with you the link to the hackathon. So I think you might be familiar with the data. So I don't want to give away too much, but
okay.
yeah. So this is that one. Nope. So if you fancy having a go, so that's the information where you can find the data. And if you want, we have a bit of a platform going where people are submitting the results. So I'm just gonna forward you. That's like the main repository that we have for the event. So you just scroll down at the bottom, you can find the data, and you can also find a platform where people are submitting the results. So that's what we're doing at the moment when it comes to the hackathon. And I think with this talk, people should be able to try and use some of the stuff that you mentioned and basically do some transfer learning.
That'd be cool. Great.
That was cool.
Okay.
Okay then. Thank you so much, Greg.
Yeah, thank you, and good luck, everyone. Let me know how it goes.
So yeah, thank you so much.
All right, take care.
Ciao, ciao.
Bye.
Bye-bye, everyone.